Okay, so let's look at this problem. We have two parallel plates. Let's say the ground lower one is at potential 0, the above one is at potential V0. We keep fixed. It's filled with a dielectric, two different dielectrics. It goes to infinity. So what is the potential everywhere? Let's try to find what are the field lines in this interface. In which direction do they bend? So let's choose the coordinate axis. Let's say this is my z-axis, this is x, this is y. The potential will not depend on x because in the x direction we have translational symmetry, nothing changes. So it will be a function of y and z. We need to solve the Laplace's equation. D squared v by del y squared plus del squared v by del z squared. This should be equal to 0. Sorry, not yet. Well, the electric field we can always write as minus the gradient of the potential. But the divergence of the displacement field is equal to 0. So the divergence of epsilon times minus 1 times the gradient of B. This is equal to 0. Now we need to split it into two regions, region 1 and region 2. In region 1, let's say this is my region 1, this is my region 2. In region 1 and 2, epsilon is constant. It's the same, it's a different constant, but nevertheless, in each one of these regions, it's a constant. So in both regions, the Laplacian of V is equal to 0 because of this. Not throughout my region, but in region 1, V satisfies the Laplace equation. In region 2, it satisfies the Laplace equation. In the interface, it will not satisfy the Laplace equation, because there will be these bound surface charges in that region. Now we can use the separation of, so this equation just tells me that del squared V by del y squared plus del squared V by del z squared, this should be equal to 0. Now I can use the separation of variables. V will be equal to a function of y and a function of z. And each one of them will satisfy this equation. Y double prime over y is C1. Y z double prime over z should be equal to C2. And C1 plus C2 should be equal to 0. Now, should we take them positive, negative, or all of them? We should look at the boundary conditions. And of course, just keep in mind that in region 1 you can have one C1, in region 2 you can have some other C1. But what do we know about the potentials? What can you say about these functions y and z? First of all, z, when z is equal to 0, should be equal to 0. Because z is equal to 0 is our 0 potential. Z is equal to, let's say, h is not our 0 potential, so we cannot really put a boundary condition there yet.
Why is it even? Why is it even? Minus 1. Minus 1 equals 1.
Y is not even, because in these two different regions have different dielectric constants. The potential need not be symmetric or antisymmetric. What else do I know? When V not for z, but I also know that v, when y goes to plus or minus infinity as a function of z, should be, no. You see, I have these infinite plates. The plates go to infinity. They go to infinity as y goes to infinity. And at y goes to infinity, well, let me look at these two different cases. No, I don't need to look at those two different cases. I have the interface over here. I'm infinity over there. I go to infinity in that direction. I will not see this interface anymore. What I will see at that distance is just my dielectric field, my capacitor filled with a dielectric. Lower plate is at potential 0, upper plate is at potential Z, V0. So when y goes to plus or minus infinity of Z, the potential should be V0 over H times Z. Whether I go to plus infinity or minus infinity, doesn't. Y goes to plus infinity or minus infinity doesn't really make any difference. Do you see why? You see, I have this my parallel plate capacitor. I have my interface over here. And I'm looking at it at that point, very far away. That very far away point will not feel this interface. So what I will see is zero potential and V0, and this dielectric fills it uniformly. And it's infinite. I'm away from the edges. There are no edges, in fact. So there are no fringing effects. So the potential electric field should be linear, vertical, constant. So potential should be linear. And at the lower plate, it should be at z is equal to 0, it should be 0. At z is equal to h, it should be V0. So if I'm very far away, this should be the form of my potential. Now I will do a trick, rather than continuing with the separation of variables. I will define V tilde, which is V minus V0 over H times Z. Laplacian of V tilde is equal to 0 in both of those regions, because that term, the addition of this term that I subtracted, has 0 Laplacian. The second derivative with respect to Z will be 0. But now this time V tilde has simpler boundary conditions. You see the boundary conditions for V tilde. V tilde is equal to 0 here, V tilde is equal to 0 there. Because when z is equal to 0, V tilde is equal to V at z is equal to 0, but V at z is equal to 0 is already 0. V tilde at z is equal to h is V at z is equal to h minus V0, but V at z is equal to h is already V0. So the difference is just 0. Furthermore, V tilde, y goes to plus or minus infinity as whatever the value of z is, this should be 0. So I will do separation of variables for V tilde. I'm not doing this separation of variables here. I'm not doing this one, but I'm doing the separation of variables here. And now y double prime over y is equal to C1. Z double prime over z should be equal to C2. But note that as a function of y, as a function of z, at z is equal to 0, this should be 0. And z as z is equal to h, this z function should be 0. So the z function should be periodic. You see, if C2 is positive, then I don't have a solution that repeats it, that takes the value 0 at two different points. It can take the value 0 only at a single point. So that tells me that C2 should be equal to minus some number. And so C1 plus C2 is equal to 0. So C1 should be equal to some number squared. So I know the solution z of z should be equal to ak sine of kz. Well, I already used the boundary condition that at z is equal to 0, this function z should be 0. I didn't add a phase. Or the cosine is also a solution, but that doesn't go to 0 at z is equal to 0. Secondly, y of z, y of y, should be equal to bk times e to power ky plus ck times e to power minus ky. Not necessarily. You see, I have divided this into two regions, region 1 and region 2. And region 1, in region 1, I have the limit y goes to minus infinity, let me call it region 1. Y can go to minus infinity, this should be equal to 0. So this tells me that the y function in region 1 is actually bk times e to power ky. And in region 2, the y function, as the coordinate y goes to infinity, this should go to 0. So this tells me that the y function in region 2 was equal to ck times e to power minus ky. Well, if I had a point charge over there with vacuum everywhere else, then I would say that y is symmetrical. But in this case, since I have different dielectrics in the different regions, this function y need not be symmetrical. There will still be some kind of a symmetry.
Is this valid? Can you separate regions anymore?
Yes. You can separate the regions whichever way you like. Of course, you have to match your solutions in these two regions.
So it has to be continuous.
It has to be continuous. Well, there are the continuity and discontinuity conditions for the perpendicular, horizontal components of the E and D fields that we have to still use. We will be using them now.
For y, for the function y.
Hmm?
It should be continuous at y is equal to 0, right?
Yes. The potential should be continuous at y is equal to 0. But the derivative need not be continuous. In fact, the derivative will not be continuous. We will see. So let's see, the z, when z is equal to h is also 0, this tells me that k should take the values n pi over L, n pi over h. These are the possible values of k. Not all values are possible. So now we have the potentials in these two regions. The potential in region 1 is sum over n, a n times sine n pi over h z times e to the power n pi over h y. And the potential in region 2, this should have the form n times bn sine n pi over h z e to the power minus n pi over h y. Now let's see, V1 at y is equal to 0 should be equal to V2 at y is equal to 0. Well, this tells me that sum over a n sine of n pi over hz should be equal to sum over n times bn sine n pi over hz, and which basically tells me that an should be equal to bn. As you said, the potential turned out to be symmetrical. Now we have one more condition. You see, in this region, the divergence of D is equal to 0. There are no free charges anywhere. But this tells me that the perpendicular component of the displacement field is continuous. The change across the surface is 0. But this tells me that epsilon 1 times E1 should be equal to E1 perp should be equal to epsilon 2 times E2 perp. This tells me that epsilon 1 times del V1 over del Y, evaluate that Y is equal to 0, should be equal to epsilon 2 times del V2 over del Y, evaluated that Y is equal to 0. Well, you see, these are continuous. Epsilon 1 perps are not continuous, so there's a discontinuity, there's a bound charge. Well, now we will have this funny result that if you just take the derivatives, sum over n pi over h times sine n pi over h z is equal to sum over n bn times minus n pi over h, not h bar, h, times cosine n pi over h z, no sine. This tells me that an is equal to minus bn. But at the same time, an is equal to bn. So an is equal to b and this is equal to 0. This tells me that v tilde is equal to 0. This tells me that v is equal to v0 over hz, no fringing effects. At the junction. So there are no fringing effects there. The only cause of the force is at the edge, it seems.
You said the potential doesn't depend on the Y. I don't understand how it implies that there's no changing effect for the electric field.
Well, you see, V is this one. So we can calculate. Do you agree that V is exactly equal to this one? Well, the electric field is equal to minus the gradient of V, which is equal to minus V0 over H in the Z direction. It is uniform. So no fringing effects.
We can also say that there is also no boundaries.
Well, there are boundaries, many boundaries. There's the boundary between the interface, there's the upper plate, there's the lower plate, there's the boundary at infinity. All of them are boundaries. So going back to our interpretation of the forces, so there are no fringing fields over here. The force is basically created by the fringing fields at the end of the capacitor. Is there a surface bound charge at the interface here? Yeah. Yeah, there is a jump in the electric field, basically, if epsilon 1 and epsilon 2 are different. If the electric field jumps, is there a jump? Sorry, hold on. Did I do a mistake over here? This is epsilon 1 times this one is equal to epsilon 2 times this one. So epsilon 1 times an is equal to minus epsilon 2 times bn. And n cannot be equal to 0. Yeah. Still the solution an and bn, they are equal to 0. But you see, electric field is constant, the same thing everywhere. There is no jump in the electric field. If this result is correct, which I still have some suspicions. So electric field is uniform, it's the same everywhere, it doesn't have any component perpendicular to my plane. So there are no charges on the surface. I mean, there are no charges on this interface between these two dielectrics.
I have that E2 over E1 is equal to epsilon 2 over epsilon 1.
Hmm?
Or maybe it's separate. So I'm saying from the continuity.
Well, you see, you told me the continuity that epsilon 1 E1 and should be equal to E2 if they are perpendicular. And that's actually...
D1.
Hmm?
D1.
No, these need not be equal.
The perpendicular component.
The perpendicular component, you see, E1, the parallel component, should be equal to E2, the parallel component. Okay? And you are saying that epsilon 1 times D1 should be equal to epsilon 2 times D2. The perpendicular components. What we found is that these are both 0. But you see, the perpendicular component of D, the discontinuity, will be proportional to the free charges. There are no free charges, so the perpendicular component should be continuous. The discontinuity in the perpendicular component of the electric field will be proportional to the total charge, which is the sum of free charges plus the bound charges. So if you know the electric field, if you know the perpendicular component of the electric field, and if you have a surface, and if there's a jump in that component along that surface, then that tells you what is the total free plus the bound charge density is. But in this problem, we found out that there is no discontinuity in the perpendicular component of the electric field is 0. That's what we found. In both sides of the surface, so there's no charge density on the surface.
We have the local force.
Do you?
The local force is proportional, is equal to proportional to the magnitude of the electric field times the gradient of epsilon.
So you're saying that the local pressure, let's say small f, is proportional to E squared times the gradient of epsilon. And on the interface, the gradient of epsilon is non-zero. So what's going on? Which is definitely non-zero. So there should be a force, but we had just found that the electric field is only in the vertical direction, and hence it can only create a force in the vertical direction. It will not create a force in the vertical direction, but it cannot create a horizontal force. So what are we missing?
Polarization bu şeyler diyalektrikteki şeyler kendileri ekvaya olacak.
But that is all parameterized in epsilon. all those effects of the polarization, we already took them into account. Can we apply the derivations in the book into this system?
The example is applied.
In an example in which there is a capacitor and a dielectric, right?
There's an interface between two dielectrics.
Okay. Where are these dielectrics? In between a capacitor, right? No?
There's some electric field, it's not specified. There's
Mhm,
also
mhm. You see, I don't think we have actually missed anything in this derivation. You see, the problem is, in the derivation in the book, it's a realistic system in which you have the surface integrals which you set to 0. Here on the surface, the fields do not go to 0. So you cannot set those surface integrals to 0 in this derivation, in this case. You see, we didn't take a finite capacitor, we took an infinite capacitor. So even if we set the surfaces to infinity, we cannot set the potential, neither the electric field, to 0 at infinity.
So here there's no force.
Hmm?
So here there's no force whatsoever.
Here it turns out that there is no force. I mean, I stress the fact that it turns out, because I am also suspicious about this result. But that is what I found. And you see, this is the solution we have for the V field. So V is equal to V0 over H times Z, and the E is equal to minus V0 over H in the Z hat. Maybe we did something wrong in the derivation. Let's see. You see, what do we know is that if you've come up with a function that satisfies our differential equations plus the boundary conditions, then that is your solution. Nothing to do. Well, the divergent curl of the electric field, it is 0. Its electric field is constant. All its derivatives will be constant. Well, the displacement field in region 1 will be epsilon times E, epsilon 1 times E. And the displacement field in region 2 will be epsilon 2 times E. So, and the divergence of the displacement field 1 is equal to the divergence of the displacement field in region 2, which is equal, both are 0. It is in both regions, I satisfied my equations, differential equations. Let's check the boundary conditions. One is V as a function of y and z at z is equal to 0. This should be equal to 0. Check. This is satisfied. V as a function of y and at z is equal to h. This should be equal to V0. Check. And the parallel component of the electric field when y is equal to 0, it should be continuous. Check. No problem with that. And the perpendicular component of the displacement field, y is equal to 0. It should be continuous because we don't have any free field. Well, the perpendicular component of the displacement field is 0. It's parallel to the interface. Check. So it satisfies all the boundary conditions. It satisfies our differential equation, so it should be the solution.
What about at infinity?
Well, at infinity, V as a function of z, when y goes to infinity, plus or minus infinity, we have these two parallel plate capacitors. It should be V0 over h times z. Check. It satisfies all the boundary conditions. It satisfies our differential equations. By the uniqueness, it should be the solution. So there are no fringing effects.
If we move the interface, since it's infinite,
The energy doesn't change. You see, if you move the interface, since it is infinite, the energy doesn't change.
and therefore
There's no there don't need to be any force. Of course, it contradicts with the result of the book. And my claim is that, it contradicts with the result of the book because the assumptions under which that result is derived does not hold here. And that assumption is that at infinity you don't have any potential. You see, that is also agrees with our conclusion that the force is basically created by the edges. So if you don't have any edge, there is no force. Ends of the capacitor, if they don't exist, then there is no force acting on the system.
Why we don't have fields?
Well, I also expected some fringing fields, to be honest. He also expected some fringing fields in the other direction. It turned out that there doesn't have any fringing fields. I don't really know. I cannot claim. I mean, the only answer I can give is that it turned out to be so, which, if you ask me, is not really an answer. Apparently, it seems that if you just imagine this as two different capacitors, each capacitor has its fringing fields. And, of course, these fringing fields will have horizontal components. So apparently, it turns out that those horizontal components, they just cancel each other.
But do we know they are symmetrical?
Well, you see, we can think of it in this way. We just found that the electric field in both regions should be the same. Right? So, which basically means that the surface charge density, the total surface charge density, the free plus the bound, in both regions, in the region 1 and region 2, they have to be the same. But that is just a plane with uniform surface charge density. There are no fringing fields inside. Now, this is an answer I prefer. You see, since the electric field in both regions turns out to be equal, you see, what we said was, okay, initially, without the dielectric, let's say, is very large, so the charge is basically uniformly distributed over the plate. When we put the dielectric, it will be polarized. So if close to this positive plate, there will be a surface charge, surface bound charge, which will be negative. So some of the charges will move from the region where there is no dielectric to the region where there is a dielectric. And the amount that moves perfectly cancels this, this bound charge density so that the net charge density in both regions is equal. And since they are equal, it's a uniformly charged system, uniformly charged surface charge density, and hence no fringing fields in between. And that also explains why we don't have any fringing fields, why the potential is just as if it's an infinite plate, etc. Any other questions?
We just deduced that there's no fringing when the capacitor is infinite.
Yes. The capacitor is infinitely long. Half of it we put one dielectric, on the other half we put some other dielectric.
And the derivation in the book fits the case where we have finite capacity.
Yes.
So there is a fringing field
In the finite capacitor, yes, there will be.
in the middle at the interface.
In the interface, there will probably be a fringing field also there, and the direction will depend on which end you are closer to.
You say you test which one?
Which ones?
You're saying we said we don't have.
Well, you see, what we know is if we have a uniformly charged infinite plate and another uniformly charged infinite plate, in this region there are no fringing fields. That we know. Well, we can imagine this system as just cut the capacitor into two, where you have one semi-infinite capacitor and another one semi-infinite capacitor. Both of them will have fringing effects at this point, but the total electric field, which doesn't have any fringing effects, is just the sum of these two electric fields. So one capacitor creates an electric field line in this direction, bulging outside. The other also creates an electric field line, again bulging outside. That will be symmetrical. So one will have a horizontal component towards the left, the other one will have a horizontal component towards the right. When you sum them up, the horizontal components cancel each other.
The derivation in the book, it does not regard where we are in the capacitor. It's just we have a finite capacitor, so the surface integral at infinity is 0.
Okay.
And also we have a derivative for epsilon.
Mm-hmm.
Therefore, we must have a force. If we have a force, then we must have some, right?
Yes.
And it's always in the same direction, regardless where we are in the capacitor, as long as we have the same electric field.
That I have some doubts. Let me look at this case. What is the direction of the force acting on this system? It will pull it inside, right? Where will be the direction of the force now? Well, of course, this is not opposing your claim, because in this first case, there will be now I will have this opposition.
Maybe there should be any force.
Hmm?
Because far away from the capacitor, we don't have any electric field, so we don't
True.
know if epsilon is changing.
Now, of course, in both of these examples, what will happen is that, okay, due to the fringing fields, we will have a force on this surface and also on this surface, but on the left surface in the first image, the force will be smaller than on the right-hand side, so the right-hand side wins. In this case, the left-hand side is closer, so the electric field there will be larger. So what wins is the left-hand side wins, so the force is toward the left. And in your case, what you are saying is, let's say, we have this system. Epsilon 1 and epsilon 2. So which way will be the force? But you see, you have to take into account the forces acting on 3 different surfaces. Surface 1, surface 2, and surface 3. So that is why I still will, okay, the force on surface 1 maybe will not depend on where you are. But the force on surface 1 and 2, it will depend on where you are. So you see, for example, if surface 1 is already inside, if surface 1 is, let's say, over here, it will exert a stronger force in that direction. So that is why I still think that it depends on where the dielectric is inside the capacitor. Not because the force in surface 3 depends on that. The force on surface 3 will not be dependent on that, but the forces on surface 1 and surface 2 will depend on where the dielectric is inside the capacitor.
So now that we agree that we have a force at the interface between dielectrics,
Yes.
we should find the reason of this force, the charge.
Well, in this case, you mean the force acting on S3. Well, which doesn't depend on the fringing effects. Yep. You see the problem? You see, at first my claim was this one. So if you have some dielectric region, there will be fringing effects. So if you put some interface over here, you put these 2 dielectrics. It will pull that surface inside, right? Well, it will depend on the polarizability. This is epsilon 1, this is epsilon 2. There are some fringing fields around, so the fringing fields are, the electric field at these points are slightly in this direction, and the electric field here are slightly in this direction. So on the interface you have some, okay, so this is the positives, this is the negative. Let's assume epsilon 1 is larger than epsilon 2. So there will be slightly, so at this point, let's say this will be the positive, this will be the negative charge. So the lower region will be slightly negative charge, and the positive charge, the upper region, will be slightly negatively charged, the surface. So the surface you will get some negative charges, some positive charges over here, right? This is the negative plate. This is the positive plate. Am I doing something stupid? Epsilon 1 is larger, it's more polarized. Yeah. On the surface. And, well, okay, it's kind of complicated because now there are 2 different forces. There will be a force acting on the interface, there will be a force acting on the top and the bottom surfaces also. So the force acting on this interface only, let's say, will be repulsive. It will be pushing it out. Of course, there will be other forces at the top side and the bottom side which will be pushing this dielectric to the inside, but at the interface, the force will be pushing it out. That is in this direction, because that is the direction of the gradient of epsilon.
That's the opposite direction. It's minus.
So it will be pushing it out. So let's look at the similar system over here. So the electric field here is in this direction, the electric field is in this direction. So here at the interface, plus minus at the interface. Over here, no, let's see, this is the plus, the electric field. This is plus, this is minus. And this is minus, this is plus. At the interface, the lower limit, the lower edge will be slightly positive. The upper edge is slightly negative, if this argument is correct. Çıkacağız şimdi. So it seems that it is again towards the outside, right?
So which one is E1, which one?
E1 is the left-hand side, left one.